So it's really art. If you look from it the more social aspect, there are some discussions because in this type of research we also use sometimes animals. So there is the social aspect as well. And then after all there's of course real science, and it's really exciting. Let's go there for it. And the color is different from blue and white, we go now to grey and yellow, but that will not be all colors you will see, there will be more. Now, realize electron microscopy and biology, it has an enormous impact on biology. Since we have electron microscopy, we could really zoom into cells, so your bodybuilding blocks of life. We can zoom into a skin cell, a muscle cell, a bone cell, and we can actually see subcellular structures like the nucleus, which contains all the genetic material, the mitochondria, which power the cell, and there's a whole load of other organ systems within the cell that are necessary for functioning. And we can see that in the electron microscopy. Now, if you look now at the right panel, there's a little bit that the magnifications we are thinking about. A frog, as you can see with the naked eye. When you look in the pond, you can see it. It's about 4 millimeters. But then when you go down and you look at, for example, a human oocyte, a human egg, you cannot see that one with the naked eye. It's even hard to see it because it's inside your body. But you take that. But if you put it in a light microscope, you surely can see it. Now, then you have that cell there. Okay, oh, that's wrong. That thing. That's the cell with all these organelles in. You can see it with the light microscope, there's not a lot of structure. But then, if you move to the other one, the electron microscope, you can really dive into actually even the molecules that make up these different organelles. So that's actually power. Now there's a new development, and I don't know a lot about it, but I want to tell you anyway about it. There is something like super resolution microscopy. It's a light microscopy, but they have techniques to actually even enlarge it more. You cannot see a lot of detail. It's a kind of seeing nice colors, like fluorescent. So it's not to study detail, but we can go with very high magnifications now with light microscopy as well. Okay. Now, how can you make something visible? You need a source of energy. You need electromagnetic waves. So it's like this. Now, one part of the electromagnetic spectrum is light. Yeah? That's very, very tiny part. That's this. And this tells you something about the wavelength. The electromagnetic spectrum is about waves. And if the waves are very long, you have radio waves. And if the waves are about 1 micrometer, we are in the light range. And if the waves are only like in the nanometer range, we have electrons. Now, what we can do is we can use light, this, and then the waves are a little bit bigger. Now, what can we see with light? The resolution, that's 2 points next to each other, which can still be visualized as 2 points. So the minimum distance between 2 points, you can still see as 2 points is resolution. Now, resolution depends on wavelength and on the quality of the lens, of course. That's also key. Now, the wavelength of light is relatively big compared to electrons. It means that the resolution is not that good. So, light microscopy, LM, resolution is up to 2 micrometers. That means when points are 2 micrometers from each other separated, you can see still 2 points. If it's 1 micrometer, you only see 1 point. For electron microscopy, it goes all the way down to 0.05 nanometer. So we are on nanometer scale. So micrometers, that's like if you take, no, that's not. But what specific restrictions have we if we use electron microscope? What is a big disadvantage? Anybody an idea? Compared to light microscopy. die. So, and you cannot even see a tissue with electron. It's not dense enough. You have to make it kind of heavy metal to be visible. So these lens are not living. While if you're a light microscope, you take a cell which divides and you can look at it while it's divided. Now here's kind of idea. The left panel light microscopy. It's not only the microscope you maybe had in secondary school, there are also all kinds of techniques. Very interesting. And we're not going into it. We hear the super resolution. You see blurry pictures with high magnifications. But what we want to focus on is, okay, that electron microscopy. Now, there's two ways. You have either scanning electron microscopy, SEM, that's surface exploring. You look at the surface of something. And what you see here, that's actually the lining of your, let's see, trachea, your windpipe. So it looks like that. With these sweeping cilia which can move out all kind of dust. On the right, it's actually a cross-section through it, as if you look in a light microscope, but now in the electron microscope. And that's what we call transmission electron microscopy. So you actually look through it. What's not really here is the color. That's just computer stuff, because electron microscopy always gives black and white. So, okay, now, we are not doing these techniques in biology just because it's techniques. We use it. Now, and one aspect you can study, and which I think is very interesting, so I use it as an example, is studying cardiovascular disease. One of the leading causes of death in the, let's see, Western world. Atherosclerosis, cardiovascular disease. And we know a lot about it, among others, because of electron microscopy. And what you see here on the right panel is a cross-section through a human blood vessel, a little bit medium-sized one. And over here you see what we call a site of endothelial injury. Endothelial cells are the ones who actually kind of smoothly cover the inside of your blood vessels. Now, in general it's fit, but not always. Over here we have a site which is not that fit. And what's going to happen is that at the end, and here we're talking about 30 years in between, it could be that lipid starts to accumulate over there, the blood vessel narrows, and that's where we have real cardiovascular disease. Now, in the timeline, okay, this is like widely in the beginning, starts around the 20s. Then, a little bit more advanced stage with a kind of sturdy cap over here. In the 30s. And then, in the first stage, you see all kind of debris here because cells here die. And this cap becomes very sensitive for rupture. And if it ruptures, thrombus can form. So it's blood platelets that then coagulate, and as if it wants to seal a wound. But you can imagine if that happens in the blood vessel, it can get loose, and it can disturb circulation somewhere else. So this is a process of cardiovascular disease. Now, light microscopy. What can we see? Beautiful picture, but not a lot of details. Look at that. Here we have a cross-section, so this is the blood vessel with a section like that. Over there, nice 3 layers. Over here is the middle layer. This is what we call the internal layer. Normally it's very thin, but in this situation, it's cardiovascular disease, it's thicker. What we see in this one, so that's over here, this layer, there's a lot of cells which don't belong there. It's smooth muscle cells, and there's a lot of lipids over there. Why? We know what the colors are doing. You stay. That's the media, the layer around it. It's all muscles, so for the pulsation of the blood vessels. And at the end, here we have a sturdy fibrous layer, the adventitia. So this is a blood vessel with a lot of lipid accumulation and cells which don't belong there over here. Okay. Oh, this is terrible, isn't it? Yes. This is actually a summary of what we now more or less know already on molecular level about how this whole process works. Don't worry. You only have to look at this one. This little tiny LDL. It's called low density lipoprotein. It's a carrier in our bloodstream for cholesterol. And LDL can actually end up in this inner layer of intima and just move across the boundary layer. How do we know this? This is not a cartoon. This is real. But here we have cholesterol, LDL a little bit more, right here. There's some proteins you always need to attach to something so that it can deliver its cargo. There is a surface which actually lofts on the outside water so that you can transport in the blood. And there is this internal core which is very loaded with lipids. And among others, cholesterol in its most fatty form. Its most fatty form is cholesterol esters. Now, how do we know that LDL accumulates in the vessel? And there we get the ethical aspect. To study it, you actually need animals. So what type of animals do we use? In the 90s, we used rabbits. So that was when I was still doing research. Rabbits, because rabbits actually have a similar process as we do, and there are also strains of rabbits who have a disease, like we have in humans, also hypercholesterolemia. So this nice pet-like rabbit, I know, what you can do, you feed them high cholesterol. Of course, it's not a hamburger what you give them. It's kind of animal food with a lot of fat in it. And then you look what happens. And you study it down with an electron microscope. Now here we have purified LDL, these little droplets over there. Here it happens to be human, but the rabbit looks exactly the same. What happens now if you infuse a rabbit with a high dose of LDL and you look after 2 hours, what happens to the vessel wall of this rabbit? Now, okay, I think this needs a little bit explanation. This is a deep edge electron micrograph. It's a transmission electron. And what we have done here is we've taken part of the rabbit's vessel wall. We actually froze it ultra rapidly fast because then you actually preserve the structure as if it's 5 minutes. The structure as if it's real, so it's instantaneously fixed. You put it in a chamber under vacuum and you evaporate the water in it, so all the structures that are in the vessel wall become visible. You cannot see that in an electron microscope. So you make a cast of platinum on it. So it's a kind as if you have a cast. So it's a mirror of it. You digest all the tissue because you cannot use that in the electron microscope. And you purely look at the cast of platinum. And you investigate that in the electron microscope. And you see this. Takes about half a year. Here we go. Go back. Okay. Okay, right. This is an endothelial cell, so that lines the blood vessel. This is the outer layer of endothelial cell. It's all kind of molecules on the outer surface. And this is the intima. So the first layer of the red vessel underneath the endothelium. And if you enlarge, you see this. This is a control on the left. You don't see anything there. On the right, you might also not see anything. But if you're trained, you see stuff. The ones with the arrows there. You see that one? That's LDL. Great. And there's 3 more. So this is really, really great when you find this, but you can see the problem already. It's high magnification. How do you find these things? How do you know I'm at the right spot of the vessel wall? And there we have 3 minutes left to discuss new techniques. And I'm not familiar with them. I just studied them from the book and I got some very nice slides from the department here in Utrecht. So, conclusion, high concentration of scanning, and you can already recognize, because now you're already trained, that this is a vessel. See, here we have a line. And here we have a fatty streak over here. You see this just with this scanner. And now the exciting thing of this new technique is that you can start digging holes in certain spots in this vessel wall. Actually, this is a healthy part. This is a part where there is loads of fat accumulation, and this is the transition part. And you can study these 3 spots very selectively, because you look for that in your wall. Now, when you make such a slide, it looks like this, okay? And how can you get 3-dimensional information? Now, there we go. See? That's the scanner. So it looks at slide 1. Now the beam comes. Some tissues taken away, and we look at frame 2. Then the beamer goes again, and we look at the 3rd frame. We have already 3 sections. And you can do this, of course, layer by layer by layer. You put all the information in the computer data analyzer, and you can make a 3-dimensional image. Okay, except that we can also detect proteins in 3D. So there we go again. This is another thing, you know. Here we have all kinds of proteins which play a role in movement of cells into the vessel wall. Doesn't matter actually. But here we have one of them. It's called intercellular adhesion molecule 1. That's for the experts. The rest say it's just a sticky protein. And then what you do is you have here a specific marker that only binds to that protein. And we have gold on it, because gold is something you can see in the electron microscope. Now, the vessel, you label it on the inside. Wherever you have this molecule gold appears, you make sections of it. Here are bigger piece, and you can analyze it here. This is a regular transmission electron microscope, and this is the exciting microscope we just saw. Now, if you do that, and you look at different slides, now I look at words. What can I point to? How can I make this now work? Because normally I have like, can do it like that, with this mouse. Okay. See, these are all these slides, and if you move through them, you go through the cell in layers. And the yellow dots there is the gold. Just take your time, look at it. We've plenty of time. This is the next cell. That's the purple, that's cell number 2. It's just the way the computer can analyze it. Okay, it's almost done. There we go. You should spend some time on it if you don't have all these things. And then, if you take all these slides and you project them on each other, and you look at the surface, the yellow dots here is the label. This is healthy tissue. We have a few of these adhesion proteins. This is a lesion. We almost have nothing. And in the region that forms the boundary, the shoulder here between the lesion and the healthy part, we see loads of this active protein. So this is a way we can visualize specific proteins, and then we can study the role it plays in this process. So there you go, the conclusion of today. With current day technology, it's possible to zoom in on selected areas of interest in biological tissues. If you like, you can use another tissue. I think the vessel wall is fine. With biomarkers, and this is this gold thing which labels the proteins, it's possible to study selected molecules and their possible role in the development of, among others, cardiovascular disease. You can also study other diseases. And with that knowledge, we can actually use to develop new drugs and treatments. So that's actually the message I want to give. I think the electron microscope brings a lot of valuable knowledge, technology into our study in biology. And this is acknowledgement. I got all these data here from Utrecht from my dear husband, Dr. Patricia Post, and his co-workers. And prior, it was the Department of 90s. These days we do far more investigations on mouse. In the 90s there were not that many mouse strains yet which would develop cardiovascular disease. But we now have mutants, mouse mutants, with specific mutations in their DNA, which make them possible to study it also in mice. So it's still animals. But there is a question, is it good or not? It also helps to cure people. So yeah, that was mine. Yeah.
Well, maybe what you just said, why wouldn't it be an ethical choice to study tissue of people?
Yeah, that's true, but do you want to, let's see, that I think we almost go in the area of human trafficking. Because you would need a person who actually wants to have his or her vessels removed. You could do that even without killing a person, but it's not something you would do, I think, to a healthy or a diseased person. And if there is really a disease, the vessels might not be that worthwhile. Yeah.
What about using recently dead cadavers? So, somebody knocked over and they're a donor.
Yeah, it's true, but you can still not study the real process by manipulating certain criteria because you want to find a question. Yeah, you're right. There's of course also,
what I would like to add to that is that I think that as Patricia says, you want to study the process, and if you do something like that in a rabbit or a mouse or a rat, the process happens within, let's say, a year. But if you would want to do it on a person, within one organism, that's not really possible.
Yeah, you're right. It's a very good point.
2-3 generations of researchers.
And how can you know that the process in the rabbit or the mouse knows what happens in the human?
You never know.
Actually,
How
close
is the process in the rabbit and the mouse?
How close is the it looks the same, but it develops faster in a rabbit. So there is this genetic difference. Yeah. But how close? You can never extrapolate it completely to people. That's right. That's for sure. But that's with most, let's see, research in biology the case. Yeah.
Well, that was actually my question because what I learned is that rats are in many cases much more close to humans than any other experimental animal. So why were they not mentioned?
Because we have actually, I don't, as far as that, I don't know no mutant rats that are useful to study this. Only mutant mouse. Yeah.
And are they working on a new rat model?
Not by my knowledge, but it would be a good one to check. And of course we also do a lot of research on cultured cells, but then it's a selected group of cells. So a lot of in vitro experiments are done as well. Okay, yeah.
I was wondering, so you send a beam of electrons into the tissue, and how do you actually get an image? Do you have a detector, or do you just get an image?
Yes. You get an image because you are not looking at real tissue, but you are either looking at a cast of it, or you're looking at tissue that's kind of stained, impregnated with heavy metals. And all the water in the tissues is replaced by plastic. And then it scatters the electrons, bounce on these heavy metals and start to scatter, and that's actually what you then, you can form an image from that. You see it?
Yeah.
If you do the part where you take up the slides, make it 3D, how much time does that take? If you, for instance, need like a centimeter of tissue, how much time does the machine?
How much time? I don't know that answer. I think it's relatively fast because the process of beaming away something with these ions, I think when you saw the time kind of lag, that's more or less how fast the slides go. Yeah. So once you have the preparation ready, you can do that in a couple of hours, let's say that way. To get a tissue in a situation that you can look at that takes 3 weeks. Yeah.
I have a history of science question, because you didn't mention when electron microscopy started to be used.
Yeah.
That's my first one.
Yeah.
And my second one is the way I exists in our tissues was deceived. So what was one of the first sort of shocking discoveries that happened after we had this electron microscope?
The first shocking after the first electron microscope, which was, I think, about in the 1940s, it was in Germany.
Okay.
So around that time, what was the most exciting? That's a hard one.
Or one of the, doesn't
Yeah.
have to be, I'm just curious.
No, I think actually this new technique is one of those. Yeah, because it's now even, it was not possible to make three-dimensional structure pictures. This technique in biology is now exists for 6 years. It's a technique which was used in industry already for a longer time. I think to produce conductors, something like that. So it exists already for 20 years, but to apply it to tissue is an enormous challenge.
Yeah.
Because you have to make the tissue such that the picture you see is not changed from the real life situation, so that was took a long time to get that. But I think this is one of the most exciting. At least, and I'm a person in this field for 30 years. Yes, this is something where I really get excited. So maybe I'm not the average, but
We have time for one last
Yeah.
question.
yeah, I will be. Oh no, it's 9. Great. Yeah.
If you look at the biggest environmental scientific complication at the moment, you see that most imaging studies are done with focal fluorescent microscopy. Do you expect to see that electron microscopy will actually replace fluorescent microscopy in the coming years?
It will not never replace. No, I don't think so. Because if you look at fluorescent microscopy, you can still study living tissue. While if you look with electron microscope, it's always that tissue. I think you always have to take the two together to get a complete image. Yeah, it will never replace it completely. No. So, okay.
Well, please give a big round of applause.